All right, so without further ado, I'm going to actually introduce our first speaker. So first up, we have Derek Dicker. Derek is the Corporate Vice President and General Manager of Micron's storage business unit. He's responsible for building world-class storage products and value-added solution. He focuses on using Micron's non-volatile memory technologies to address the growing opportunities in large market segments, such as cloud, enterprise, and client computing. The title of his session is QLC Flash, Meeting the Challenges of the New Data Economy. This is going to be a great session. Let's give it up for Derek.
Thank you very much. So first off, I want to thank everybody for coming to join us today. As we were preparing this speech, it became really evident that we're in a super unique window of time in our industry. The products that the people in this room and attending this conference develop are at the foundation and the core of all of the critical advances that we see happening in technology today. And so what we decided to do is build up a bit of our view as Micron as to how we see the market evolving in both memory and storage, why we believe things are so critical, and spending a bit of time talking about the application of those technologies into our everyday lives. Now, before I get started, I wanted to maybe provide just a little bit of background on Micron itself. I'm new to Micron. I've been here a little less than a year, and there's a few things that I've learned that I've found particularly interesting about the company that I thought I'd be interesting to share with you. So first off, can anybody guess how old Micron is? The Micron guy sitting down here, no chance. Sorry. No dice. Shout it out. Any guess? 30. No, we're older than that. Come on. 50? Do I look 50? I'm just kidding. So we're 40. Actually, the company is 40 years old. We were founded in 1978. And our birthday, by the way, is on October 5th, so it's coming up. We're looking forward to celebrating 40 years. The company was actually founded by 4 individuals to create a design consultancy for semiconductor design. Slightly different than what we've become over time. And they were founded in classic startup fashion in the basement of a dentist's office, of all places. Now, the company ended up evolving forward into a position where they went from design, services, and consulting into wanting to build DRAM. That was the first focus area of the products. And they needed to actually source capital. Now, the company was founded in Boise, Idaho, which is not a place that's flush necessarily with venture capital or was known for venture capital in this window of time. So who do you think they went to when they needed to get an influx of investment? Potato farmer. That's pretty darn good. This gentleman is the king of potatoes. This is J.R. Simplot. And one of the interesting facts that I found about him as I was doing research for this is in 1967, he shook hands with Ray Kroc to actually supply more than half of the potatoes that went into McDonald's. But over time, he built a multi-billion-dollar business in the potato world. And the reason why it's interesting is because he actually was the first big money into the company that allowed the company to scale over time. And from there, we've actually come a very, very long way. As I mentioned, the company was founded in 1978. We've ended up starting our lineage in the DRAM space, and we're very privileged to have a number of milestones around DRAM. We migrated into NAND and created both SLC, MLC, and TLC NAND over time, and built SSD families wrapped around them. And ultimately, as several of you probably are aware, we announced 3D XPoint technology to boot. And most recently, we're proud to have introduced the industry's first QLC SSD, which I'll talk about in a little bit. But in general, the company's had just a phenomenal experience growing over time into its current role. We're about 35,000 people worldwide, and on a revenue basis, we're now somewhere from a guidance perspective on a quarterly run rate, we're north of a $30 billion company. So we've been quite happy with the success that we've had, and I don't say it lightly when I say I feel like I'm standing on the shoulders of giants in terms of the people who built the company. So that's the background of the company. Now, as I mentioned, 40 years, we've seen an awful lot. Rather than going all the way back to 40 and giving you a rendering of what we learned, I thought I'd take just a short period of time to review what we've seen happening in, say, the last 15 plus years, and do it in the context of how our industry has changed. So what we've done is we've broken this down into eras. And the very first era that we wanted to call out was roughly at the turn of the century, 2000 to 2007. And this is a PC internet era. This was wrapped around the use of email extensively for the first time, but the big innovation, of course, was the web and being able to store information on the web and create information that could be posted and seen by people anywhere in the world. And in that period of time, there was about 250 billion gigabytes that were created annually. Now, this represents, if you were to monetize this across DRAM and NAND flash and NOR, to be about $35 billion of market opportunity on an average basis. Who can guess what the next era was? Mobile. Thank you very much for the assist. In the mobile era, we scoped this as roughly from 2008 to 2016. And what you saw was a phenomenal growth from 250 billion gigabytes to 7,000 billion gigabytes, a substantial hop. And part of what came with that in terms of data created annually was the creation of, obviously, camera integration into mobile devices, and the fact that people are now able to snap photos and share information in the form of video, as well as a multitude of other applications that grew things in time. Now, this was the last era that we documented, but the new era that we see, and that I think we're all living through the midst of right now, is what we refer to as the data economy era. And we're going to spend quite a bit of time talking about this particular one. But what you can see is from 2016 to 17, from a created annually perspective, there's almost a 3x growth in the amount of data stored. This is fairly phenomenal in terms of growth. And by the way, that's just the first year in the front end of what we think will be a multi-year journey for our industry. Now, what's particularly interesting is that the revenue generated for memory, again, DRAM, NAND, and NOR, is upwards of $130 billion. Again, comparing $30 billion in the PC internet era to $130 billion in the data economy era. All of that is literally wrapped into innovation, and innovation that's driven by next generation networks and IoT, the deployment of cloud, et cetera. Now, this is just 2017. If you look at the forecast going forward, we actually think there's another 3x growth that's coming to 62,000 billion gigabytes, 62 zettabytes in 2021. So, in general, the amount of data that we see being created is skyrocketing at a crazy, crazy rate. And the question is, where is it coming from, and how can we take advantage of it? So let's go look into each of the segments that actually feed this activity. So the first one that we'd like to talk about is a client PC. If you look into the evolution of the client world, a big chunk of this historically was a desktop PC. And for quite some time, there was a lot of talk about the death of the PC. And what we found as time has elapsed is that absolutely has not been the case. We continue to see a healthy desktop business, and we continue to see the world of laptops and tablets grow. But if you kind of unpack from a storage level what's happening, something very fundamental has been shifting, as we all know in this audience, and that's the integration of solid-state technology into these devices. When we get to the outer edge of our horizon, to 21 and 22, we're looking at a scenario where we actually see desktops getting to 50% plus deployment of SSD, and mobile clients getting to well above that, approaching full saturation in terms of consumption. And so we get a blended average of about 80-ish% of anticipated adoption of SSDs. But the other dynamic, so you imagine that's going to grow your unit volume, but the multiplicative effect is that the average capacity inside these client PCs is forecasted to more than double. And some analysts will put this on the outer edge of 2021 or 2022 to be on the order of 600 to 700 gigabytes off a basis of 250-ish today. So this particular space, we're seeing a fairly large opportunity for gigabyte growth over time, particularly in the SSD domain. Now, the next platform to talk about is the mobile platform. And this one is actually astounding in terms of the fundamental shift that's coming. With the deployment of 5G, we actually see a 100x network bandwidth increase coming at us. Now, I had the privilege of spending some time with one of the world's largest manufacturers of wireless internet infrastructure over the last week in Southeast Asia. And one of the things that they were demoing to us and showing us was their vision of 5G and what deployments look like. And they're painting a vision of an average bandwidth into your mobile device of 2 gigabits per second, but a capability to deliver almost 20, approaching 20 gigabytes per second on a client. And when you sit back and you look at that and you think about what you can do with that, it's actually pretty phenomenal. Today alone, we see a fairly substantial amount of features being embedded into these devices. But if you look into the future with things like AR and VR, the delivery of high-def or ultra-high-def content into these mobile phones, you actually can start to envision that there's going to be a large, large demand for an increase in both memory and storage that sit within these devices, to the tune of almost 2x in the DRAM domain and greater than 3x we're forecasting on the NAND side of things. Now, what's also incrementally interesting is there are phones available today that actually feature a terabyte of NAND in them. That's scary. My kids, by the way, would fall in love with that option, but it's still at the highest end, and we start to expect to see that we'll continue to ramp up that growth over time. The next is automobiles. In the space of automobiles, what I find completely fascinating is the number of sensors that are being built into these solutions. We have cars today that are in pilot programs actually taking kids to school. That's just downright scary, but exciting all at the same time. The number of sensors that are being built and forecasted to be built into automobiles are going from something on the order of 10 to maybe at the high end 100 today, all the way to 200 out on the furthest edge of our forecast. And at 100 million cars being manufactured and deployed into the world, that translates to 22 billion sensors that are out there a year generating data. And that data needs to be both processed and stored, pushed to the edge, and then maybe even pushed back into the data centers for the purposes of analytics. And then before we get to the final, the data center space, the Internet of Things. Now, our colleagues from Verizon presented earlier today, and an interesting statistic that they talked about was the number of IoT devices surpassing mobile phones in the very, very near future. It's a bit scary until you sit back and think about some of the use cases that are out there from an IoT perspective. And that's starting all the way from wearables that we see fairly regularly used today to visions that I've seen portrayed where people are actually deploying entirely smart cities, putting sensors inside of things as simple as manhole covers, or wrapping sensors around cows in the agricultural industry to monitor where they travel as well as what their production looks like. It's an amazing greenfield area, but what's scary is that the data that's being generated out of these is forecasted to grow at 50 times what business data is going to look like over the outer edge of this horizon also. If you look at image sensors, we're looking at 3 image sensors for every man, woman, and child walking the planet. This is phenomenal growth that we see coming our way and represents a huge opportunity for all of us in this room. Well, the last piece is in the data center. So all of these different endpoints, all of these different places that are gathering data, be it sensor data in automobiles generated from client PCs or in mobile applications, that data is being gathered together, and in many, many places it's being aggregated up into data centers. And it's done for the sole purpose either of storage or for processing that data and doing something absolutely incredibly important, which is converting that data into information. And then taking that information and yielding results that, with a little help and effort, help to make our lives better and our businesses improve. And it's all facilitated, obviously, by artificial intelligence. And the beautiful thing about AI is that AI actually has a huge dependency on both memory and storage in terms of how artificial intelligence gets enabled. I wanted to spend just a couple of minutes looking at an example of what we think happens to server architectures in time as AI gets deployed more broadly. What we show here is an estimate of DRAM in a server. And for those of you who are in the back who might be able to see this, on the far left, what we show is that called the average configuration of a server in 2017 had about 145 gigabytes of DRAM placed in it. And a standard server in 2021 is expected to have about 366. But when you go through the process of building out artificial intelligence algorithms and deploy the techniques of convolutional neural networks or deep learning, what you find is that you actually have a very, very high requirement for DRAM. It accompanies the massively parallel set of work that gets done in a training server, typically conducted on GPUs. And what we see is that by 2021, we think the size of the DRAM bank on average in one of these AI training servers is on the order of 2.5 terabytes, which is a phenomenal growth. It's almost 7x the DRAM side. But it doesn't just stop at the DRAM side. There's also a need for local storage in these servers. And we see in that particular domain a standard server at about 2 terabytes, and we have the benefit of increased average capacities growing in SSDs to take us up to about 11 in a standard server for NAND or SSD. But with an AI training server, we actually see it approaching 20 terabytes in size. So this underlying trend, this need for more memory and more storage sitting in the AI domain is quite impressive in terms of what it represents as growth. Now, don't just take it from us in terms of forecasts. What we did is we also included a quick summary of what's going on with NVIDIA's DGX2 platform. If you're not familiar with a DGX2, this is essentially a world-class AI training server that's in existence today. And in it today already, there's a 1.5 terabyte that's enabled of DRAM. And then if you recall, on the prior slide, we showed in 2021 an average of about 20 terabytes. Today, this server is enabled for 30 terabytes of shipment. So there's a tremendous amount of activity that's going on in this particular domain that's driving up a need for more DRAM and NAND in these platforms. Now, the other thing that we've noticed affiliated with AI and deep learning that we thought we'd share, and this is more applicable to when we start talking about QLC SSDs, is that we see the I/O patterns in these workloads in the data center changing. And actually, I thought it was hilarious. If you look at this guy, he was super amazed. He's looking forward to hearing some pretty amazing data. The traditional data center, actually, we found in a couple of different published articles, sits around a 4-to-1 read-to-write ratio. But if you look at I/O patterns in the deep learning AI space, you see somewhere on the order of 5,000 to 1. Now, of course, not all workloads are going to be the same, but this does show a very stark delta and a need for things that are read-intensive in nature in evolving forward for these types of workloads. Now, the great news about all of this for us in the room, these trends that I've talked about and the demand that we see growing over time, is that there's a need to span the entire memory and storage continuum, all the way from DRAM and NVDIMM and 3D XPoint for real-time in-memory processing, scaling to the storage side of the house, which is with NAND as a primary vehicle, and of course, storage class memory as an incremental vehicle that sits between the two of memory and storage semantics, but specifically NVMe and SATA SSDs evolving forward for the storage applications. So up to this point, what I hope we've conveyed is that we see a lot of reasons to believe that what we as a community and as an industry work on, the demand for it is huge, mapping into the future. And what's going to be absolutely required in order for us to service that demand and to be able to deliver to the industry solutions is innovation. So I thought for a few minutes what I'd do is maybe provide a little bit of our view of innovation that we've applied both at the media level as well as at the system level, and then a bit about the software level before we're done. So from a NAND perspective, one of the things that we've been privileged to help innovate around is a technique called CMOS under the array. Now, what you see on the right is a rendering of a tops-down view of a die. If you're not familiar with how the semiconductor world works, in a fab, we build wafers, and those wafers are literally a cylindrical shape, very thin, wafer-like. And on those, we have die. We actually assemble and build semiconductor products. And those products are typically square or rectangular in nature. Historically, in a NAND design, what you would find is you would have an array, that's the actual memory itself, the media, and then wrapped around it, around the periphery, is logic. And that logic essentially controls the function of the device itself outside of the memory. But what we were able to do in our first generation 3D TLC work was to take that CMOS logic and embed it underneath the array. And what that does is it allows you to compress your X and Y dimensions on that die. And inherently, if you're stacking more memory over time, you get more space to actually add more memory, which results in a cost reduction and ultimately also a performance improvement based on where that CMOS logic now sits underneath the die. Now, this is something that we're particularly proud of having helped to innovate. By the way, the graphic on the left is a vertical slice, so you can see how we have metal the array structure and the CMOS circuits that are embedded underneath. The second thing that we've done is actually utilize what we call array stacking. So our first generation 3D NAND was a 32-layer design. And that 32-layer design you can see represented fairly simply in this box. When we wanted to move to 64 layers, rather than trying to do a monolithic addition of another 32 layers on top, we ended up taking that 32-layer instantiation and stacking it on top and building that into a single product. And what that did is that allowed us to take development design cycles and compress them. And it also allowed us to future-proof for what we were to build next in what's our 96-layer technology, our third generation technology. Now, these set of bullets on the right apply to the 96-layer technology that we've announced recently. We of course, got a 50% increase in layers, but because of how we structured this with CMOS under the array and the array stacking, we've ended up being able to deliver right bandwidth benchmarks. Now, this is the second time that we've done array stacking and the third time for CMOS under the array, so we think we're getting a bit better at this every time. Now, what I want to do next is I want to spend a bit of time talking about what's next. This is what we've done so far, but what's coming next is actually, I think, probably just as interesting to everyone in this audience. But before I do, does anybody remember Regis Philbin and Who Wants to Be a Millionaire? They used to phone a friend. I'm going to phone a friend. I'm going to phone my buddy Russ. So Russ, come on out. So Russ actually is here with us today. He is the Corporate VP of Non-Volatile Memory Integration, and he's going to share a little bit about our next generation NAND technology.
Okay, thanks, Derek. Appreciate the opportunity to talk to everybody about our next generation NAND. Like Derek mentioned, we are in the process of transitioning to our third generation vertical NAND technology. And in that transition, it gives us the opportunity to look back and see the success we've had in the vertical transition, which has enabled NAND to continue the historic cost and density scaling trends. That's a nice place to be, considering the uncertainty we had in the industry a few years ago as we were facing the end of planar scaling and the need to find a vertical inflection. So now that we've got through our third generation, what do we see coming into our fourth generation NAND? And I want to give you a little sneak peek at what we have coming on that. So we're going to continue the cost scaling. We're going to continue going on historic trends, and we're going to leverage those same enablers that Derek mentioned earlier, the CMOS under the array and the array stacking, because those are both excellent scaling enablers. CMOS under the array in particular, like Derek mentioned, is if you imagine our NAND array being a skyscraper, the CMOS under the array is like having a subterranean garage buried underneath. So it's a great space saver, and not only that, it allows much better efficiency in your routing into the array. So we're gonna leverage those technologies that have been successful for our first three generations of NAND, and then on top of that, we're gonna integrate a low resistance metallization, which is gonna dramatically improve their performance. With the combination of these technologies, we have the opportunity to once again stand and look out over the horizon, and what we can see is the scaling is going to continue. So we see this technology being able to scale out beyond 200 tiers, which will get us well into the next decade as far as continuing the scaling trend that we've enjoyed on NAND so far. To be specific about some of the improvements we're expecting, so with these new modules we're bringing into the technology, we're very specifically going after higher write bandwidth. So we're already benchmarking the write bandwidth, but by pulling these technologies together, we expect to drive that to another 30% improvement over where we are today, over our previous nodes. The other key point, and one that our customers are going to enjoy, is the fact that we're going to drive the energy per bit down by over 40%. So that's going to be another big performance advantage on this particular node. So the other technology that we're excited about is, like Derek mentioned, is the 4-bit per cell, or the QLC. So as most people in here know, the NAND has enjoyed its scaling trend over the last few years, partly because of the ability to put more bits into each physical cell over the years. So it started out as SLC, where you got one electron or two electronic states in the one physical cell. Those, so you're basically containing one bit of information. So you go to MLC, now you're looking to store 2 bits of information in that same physical cell, what happens there is now you're forced to have 4 electronic states. TLC, where most of the industry has transitioned, doubles that again. So now you have 8 electronic states contained inside that one physical cell. So what we introduced earlier this year was the QLC technology. So this QLC, once again, doubles the electronic states that we have to store in each of those physical cells. Not only store, but we got to be able to delineate them reliably, which is a tremendous feat. So this QLC technology enabled our first 1 terabit component. So that 1 terabit component is the media behind the first QLC enterprise SSD that we announced earlier this year. So that media was created on our 2nd generation NAND technology, but we do anticipate you will be seeing the QLC coming in on our next generation nodes as well. So with that, I'll let Derek discuss what the implications are of that QLC SSD. Thanks, Derek.
So leveraging the core technology that Russ walked you through just a minute ago from the QLC side of the house, we were able to develop the 5210 Ion SSD. We announced this just a couple of months ago, as he mentioned, at our Investor Day. And essentially the focus of this particular drive is a read-intensive focused enterprise class drive. We took the foundational elements of our 5200 SATA SSD and we coupled that with QLC NAND to give our customers a migratory path that allows them to take advantage of the economics, the capacity, the performance, the cost, and also the flexibility of the architecture in their platforms. And what we've been doing since we announced that is spending quite a bit of time working with our customers to identify what the ideal workloads are where we can get a right-sized, cost-effective performance value. And I thought I'd share just a little bit of detail in that domain. Now, we have a couple of classes that actually are going to touch this. I'll show a slide at the end to cover it in case you're interested in getting more detail. But the 2 buckets that you'll find that we're focused in are real-time analytics as well as content delivery and distribution. If you look at the first example, this is a business intelligence workload with Microsoft SQL. In this particular case, what we found is that we can achieve essentially a 5x improvement in query results with a quarter of the drives and to maintain somewhat of a similar cost profile at an overall TCO level. Now, this is a particularly powerful value proposition as you're talking to customers that are dealing with the challenges of TCO in their markets. The second is Cassandra and leveraging NoSQL. Now, in this particular case, what you can see is we started with 4 10K HDDs, and we were achieving somewhere on the order of about a little less than 2,000 operations per second. And as we started to compare against a single 5210 Ion drive with an 8 terabyte capacity, we were running almost 7,000 operations per second. That essentially translates to a 4x-ish improvement in operations per second. But the other interesting thing is when you look at the power, which of course factors into TCO, there's approximately a 10% savings associated with that. And then the last example that I'll show you, and again, you can get more information in our breakout session, is a Ceph object store. In this particular case, we built a cluster of 3 Ceph nodes and put in 24 8 terabyte drives of the 5210. And what we were able to achieve was essentially 70 gigabits per second of read object throughput. That essentially maximizes the 3 25 gig NICs that are sitting inside these platforms, accounting for the challenges of overhead and efficiency in the Ethernet protocol. But in this particular case, what we were able to do is we can actually produce out of this cluster approximately 3,000 ultra-high def video streams that can be distributed in a video content delivery network, and to do so at a phenomenal cost structure. Now, the last piece of technology that I'd like to talk about, we started with media. We talked about the media. Then we transitioned just now into workloads wrapped around systems, subsystems as SSDs. But we've also been working on a set of advanced software in the form of a storage stack. And in this particular case, what we did is we said, all right, if we can envision a storage stack that wasn't encumbered with the challenges, or let's just say the history and lineage of the hard disk drive era, what would that look like? And if we could actually envision it by having people who knew NAND, who knew SSDs, and who understood how the interaction between a storage stack and an SSD might be optimized, what would that be? And we actually chose to build that stack. And the results here are early results from work that we've been doing with what we call the Micron storage stack, where we ran the stack in a key value store with our stack underneath it, sitting on top of our 5200 drive, which is our QLC SATA drive. And then we ran it again with our 5210 QLC Ion drive. And what you can see is that we actually were able to achieve, through stack optimization, through that stack, a doubling in throughput and a reduction in write amp of almost 4.5x. So it's a pretty material improvement in the performance of the solution. And it didn't just stop there. We've actually been able to demonstrate substantial increases in operations per second, a reduction in latency, lower system write amplification, as well as reduced overall total power consumption in database applications, which is where we've chosen to start our innovative work. Now, the last piece of the story is we've actually started to engage with a few customers. In this particular case, this is the Texas Advanced Compute Center. And what they do is, and I love their overall tagline, which is, they power inventions that change the world. And what better thing to be working on in your daily life is to take the intersection of technology and to go solve real-world problems. And what they did is they implemented the Micron storage stack into their infrastructure that does weather sampling of database, a database of weather sampling. And what they ultimately do is take the weather sampling work, they try and derive information from that to predict when major natural disasters are going to occur, and then they use that information to alert the individuals that might be impacted by this. This is a field of research that's underway and has been underway for quite some time, and they're getting some very interesting results. There's nothing better than knowing that the work that you're doing actually is making a difference. Beyond the bits and the bytes and the growing of a business, being able to know that you're actually contributing to help make a difference is fantastic too. And I wanted to leave you on the last slide with our vision. This is a vision that Micron has, and I actually believe that our entire industry shares it, and it's a very unique time, as I mentioned, transforming how the world uses information to enrich life. This is something that I think we all ought to continue to strive to do. I think we're in the best period of time in our industry to be able to actually make it happen, and I'm super honored to have been here today to have a little bit of your time to tell our story. As a final slide, please, where you have opportunities and questions, come join us in our breakout sessions. There's a handful of them. We'll leave them here. And then also tonight, if you're interested, we'll have a reception at the Terra Courtyard. But thank you very much for your time.